Hey everybody, welcome back. We're going to get started with chapter 2. It's a long one, so I'm going to actually break this up into two videos, and you'll need to watch both of them. We're going to cover most of chapter 2 in the upcoming live lecture, and then the following week we'll finish up chapter 2 and cover chapter 3. So just hang on. It's a lot of math. It's not hard. But there's a fair amount of math, and I didn't want to have one super long video because that was just going to be torture for everybody. So I wanted to at least give the option of you being able to take a break and make that a little bit easier to find your place next time. So without further ado, let's move into chapter 2. So we're going to be talking about measurements. We're going to be talking about how we can get those measurements, significant figures, all kinds of things, how we can do calculations with those measurements. And in medicine, you're going to be making a lot of measurements. I mean, one example is shown here where you can take someone's blood pressure, you can measure their pulse. If you're administering medication, then you may need to measure that, or if there's a vaccine, flu shot. Those are all things that have to be measured and measured quite precisely and accurately. So learning about measurements and the units that measurements are made in is going to be really helpful if you're in the medical profession or if you're interested in it. The first section we're going to talk about is the units of measurement. So we're going to learn the names and abbreviations for the metric and SI. We're systems, we're going to talk about volume, length, mass, temperature, and time. And there's lots of measurements that you encounter in a day. You have a mass or weight. There's a temperature outside, all kinds of things. So scientists use the metric system. And in addition to the metric system, there's the International System of Units, which is a worldwide standard. Okay, and while there's a lot of overlap in terms of the measurements and the units used for the metric system and the SI system, there are some differences. So this table will be helpful to you. It shows you the different measurements, so volume, length, mass, temperature, and time. And then it shows you the metric system and SI. Let me change to black. So there are some differences, like volume. In the metric system, we use the liter, but the SI unit is the cubic meter, or meter cubed. So there's one difference here. Another difference is mass. In the metric system, we use the gram, okay? In the SI, we're talking about kilograms. It's not that grams can't be used, it's that this is the standard unit of measurement. So there's another difference. And the final difference is temperature. Typically, you're going to use the Celsius, degrees Celsius, but the SI unit is actually Kelvin, which is an absolute temperature scale. So keep those differences in mind. And we'll talk about the different types of measurements one by one. Let's start with volume. So volume is the space occupied by a substance. You'll definitely want to know that definition. And as I pointed out on the table, the SI unit for volume is meter cubed. But in the metric system, we use the liter. And to give you a kind of an idea of how big that is, it's a little bit larger than a quart. Okay. So if you've ever purchased a quart of milk, like the tall, skinnier one, that's a quart. So a liter is a little bit larger than that. Length, metric and SI systems use the meter. The meter is a little bit longer than a yard. You may not even remember what a yard is because we don't really do those kinds of measurements in school anymore. Once you learn about a ruler and how to read inches and stuff and convert between inches and feet and yards, then you just kind of leave it alone. But A meter stick is a little bit longer than a yardstick, and that's what the SI and the metric system use. For mass, we're talking about the measure of the quantity of material it contains. So how much matter is in something. For the metric system, we're using the gram, and that's used for smaller, like everyday masses, which makes sense. But if you're, say, getting the mass of a person, you're going to use the kilogram, which is the SI unit of mass. So typically in the lab, you're going to be using an electronic balance, and it's going to give you some kind of digital readout, and it's probably going to be in grams. So for all intents and purposes, grams are going to be a lot more useful to you than kilograms because you're using much smaller amounts of things. Temperature is something that we already know. So we're talking about how hot or cold something is. Celsius is what you might see if you're watching the weather in a different country. You'll also see it if you're just looking up the weather online. Kelvin is the SI system unit, and that is an absolute scale. So 0 Kelvin is 0 Kelvin. And notice there's no degree sign. For Celsius and for Fahrenheit, which is what we're used to, there's a degree sign. Kelvin is absolute, so there is no degree. Okay? It is what it is. 0 means 0. Time is, again, something we're all used to measuring, right? So you can talk about years, days, hours, minutes, seconds. For SI and metric, the unit of choice is the second, okay? So here's a learning check. What are the SI units for the following? You can pause and do this as just kind of a quick recap, just to make sure that you know the different units for SI and for metric, because you will need to know that. After you've paused and you try it yourself in your notebook, then you can keep going and look at the answers, okay? So instead of writing out all the answers, I just pulled the part of the table that has all the SI units. So you can use that to double check your work. But just make sure that you keep them straight. What units are SI units for each measurement type and which ones are for metric. So that's measurements in the different types. Now we're going to talk about measured numbers and significant figures. So a measured number is something that you're going to get by using an instrument like a meter stick or a balance, something like that. So those give you measured numbers. And we're also going to talk about significant figures. So how much can you trust that number? So measured numbers you get when you measure a quantity, okay? So your height, your weight, temperature, the mass of something that you put on a scale, time, those are all things that are measured. To write a measured number, you observe the numerical values of the marked lines if we're talking about a ruler. So think like a ruler. You're not going to have marked lines on a balance, okay? But thinking like a ruler or a graduated cylinder. You estimate the value of the number between the marks. So this is my ruler. And I had a line that I was trying to measure. I would observe the numerical marks, right? So this is 1 decimal point. And then I have to estimate between 1 and 2, kind of between these two lines to get my last digit. So that's about here. I'd say halfway is about maybe there. So maybe it's 1.4, and we'll call this centimeters, even though it's bigger than a centimeter, I could tell. So that's how you develop a measured number. You observe the numerical values in the marked line. So in this case, we saw the 1. And then we estimate the value between the marked lines. So there's nothing between that 1 and the 2. So you have to guess or estimate. The estimated number is the final number in your measurement. So in this case, we have the 1s and we estimated the 10th place. And that's our measurement. Here are some more examples of using a ruler to measure the length of an object. So here again, you're going to get 4 point something. Here you're going to be able to get 4 point something something. And here you're going to be able to get 3 point something. Okay. And that's just by looking at the ruler. So here, these little tick marks are millimeters. So that means you can get the 4, which is the centimeters, the 10th place, which is millimeters, and then get an extra decimal place after that. So A, B, and C are represented here to tell you the exact length. But you should be able to look at a ruler and know how many significant figures or how many decimal places there should be in your measurement. So we have these measured numbers. Now we need to be able to count significant figures. All the digits in a measured number are significant, including that last digit that you kind of guesstimate. So significant figures are used to represent the amount of error associated with a measurement. So if I have 4.777 centimeters versus 4 centimeters, this one is going to have more error because it doesn't have very much in the way of significant digits. There's only one significant figure, whereas here I've got 4 significant figures, and I'll usually abbreviate significant figures SF. All non-zero digits and zeros between the digits are significant figures. So if I have 4.077 centimeters, this 0 is significant. However, if there's a 0 that is a placeholder, that's not counted as significant. Okay? So let's say we had 0.192 milliliters. This 0, which is before all the non-zero digits, is a placeholder. It is not significant. Finally, when you have a decimal number, the 0 at the end is significant. So this number, 19.20 meters, would have 4 significant figures, while the number I wrote before, the 0.192 milliliters, only has 3 significant figures. Let's put these rules. So here's some examples of the rules for significant figures. And then there's measured numbers, and it tells you how many significant figures there are. So you can take a look at this, and it'll give you some more examples of how to count significant figures. I was giving you examples as I went through the list on the other slide. But this can kind of help you. You can look at this while you're doing your homework to say, okay, my number looks kind of like this, and then figure out how many significant figures you have. So those are significant figures. Now we need to talk about exact numbers. So exact numbers, they're not measured. Not measured. So they do not have a limited number of significant figures. They have an unlimited number, okay? When we're figuring out the number of significant figures to report in our calculated answer, we don't use exact numbers as part of that. Exact numbers are obtained by counting. So examples would be like 8 cookies or 6 eggs, something that you can observe by eye and count. You know for sure that there's 8 cookies. You see them right there. There's no doubt. You're not measuring it. It's an exact certain number. Exact numbers can also be definitions that compare 2 units. So if you cook or bake, you may know some of the conversions between quarts and cups or tablespoons and cups and things like that. So an example would be 1 quart is equal to 4 cups. That definition, comparing those 2 units, that's exact. Likewise, if we're using the metric system, or just the same measuring system in general, you can say 1 kilogram is equal to 1,000 grams. That's a definition of a kilogram. So that is exact. We don't use those to figure out how many sig figs to report in a calculated answer. So you'll need to be able to tell the difference between a measured number and an exact number. Here's some more examples of exact numbers. So things that you count, and then defined equalities. These equalities are going to come back a little bit later on in Chapter 2. We're going to talk about how to write equalities and things like that. Just remember that they are exact numbers. So here's a learning check. Identify the numbers as measured or exact. And if the number is measured, then you want to also tell me how many significant figures there are in the measurement. So pause it, take a second, do this in your notebook or maybe in your head, make sure that you have your answers locked, and then press the play button again to see what the answers are. A, we have 3 coins. Coins are something that you can count. That's exact. We don't need any kind of an instrument to get that number. The diameter of a circle is 7.902 centimeters. That's definitely a measured number. One of the hints is, look at the units. Centimeters, that tells you that it's a length. And length is a type of measurement. So we can count significant figures. All of these numbers, all of these digits in this number are significant. It's a decimal number. We have a 7 as the beginning. If that were a 0, then that'd be a little bit different. But 7.902 centimeters has 4 sig figs. And this last one, 60 minutes is equal to 1 hour. That's an equality. So it too is an exact number. So hopefully you got those right. If you didn't, that's okay. We'll go over more examples like this in class. So now we need to go over scientific notation because somehow it got left out of Chapter 1. But that's okay. We'll get to it. Sometimes you have measured numbers that are easier to record in scientific notation because there's a lot of zeros at the end of the number, or there's a lot of zeros between the decimal point and the numbers you're really interested in. So scientific notation has two parts, the coefficient and the power of 10. So what that looks like is this. You have some type of coefficient, and this is the power of 10. The coefficient has to be at least 1, but no greater than 10. So, if we have a number that we're trying to write in scientific notation, let's say that we have 5,021, and our decimal point is here. We need to make a coefficient of at least 1, but no greater than 10. So we're moving the decimal point, and I'll change colors here so that you can see it. We'll move it right here, okay? So that we now have 5.021 as our coefficient. Now we need to write a power of 10 to reflect how many decimal places we moved. So you literally count 1, 2, 3. We move the decimal point 3 times. So our power of 10 is going to be 10 to the third. Okay? That blue number is what I filled in. Then we have to figure out if the power of 10 is positive or negative. Look at your number. We started out with 5,021. If your number is 1 or bigger, your power of 10 is going to be positive. If your number is less than 1, the power of 10 is going to be negative. Our number is certainly bigger than 1, so our power of 10 is going to be positive. We don't have to write a positive sign. But when we put the whole thing together, our number in scientific notation is 5.021 times 10 to the third. Let's do a couple more examples. Let's write 2400 in correct scientific notation. So first off, how many significant figures do we have here? There's no decimal point, so that means all these zeros are placeholders. The only two numbers that are significant are the 2 and the 4. So there are 2 significant figures. For our coefficient, and I will add a decimal point here just so that you can see it more clearly, but there's no decimal point in the actual number, so that's why we're saying 2400, okay? But I want you to be able to see a decimal point that can move. So to make our coefficient, it has to be at least 1 less than 10. If I were to put it here, our coefficient would be 24. That's too big. Let's try again. If I were to put it out here, it would be 0.24. Too small. It's got to be at least 1. So that means that we have to go here. So our coefficient is 2.4. Notice how I dropped all those zeros because they're not significant. You only keep the significant digits in your scientific notation coefficient. Now we need a power of 10. How many spaces did we move? 1, 2, 3. Is our number bigger than 1, or is it at least 1 or bigger, or is it smaller than 1? Well, Our number is much bigger than 1. So n is going to be positive. So we don't have to do anything else. We can just write it in the correct format. Let's do one more example. We'll do a number that's smaller than 1 so you can see that. How many significant figures does it have? It has 2 significant figures. All of these zeros beforehand are placeholders. We do not count those for significant figures. Our coefficient, we're going to scoot this decimal point between the 8 and the 6, making 8.6. That's definitely at least 1. It's also less than 10. For a power of 10, well, how many decimal places did we move? 1, 2, 3. Now we have to determine if our n is positive or negative. This number is less than 1. So that power of 10, that n, is going to be negative. When we write it out, you put the negative sign in front of the 3. So this is for numbers less than 1. That's scientific notation. Simple as that. We'll do more practice in class. So for your textbook, they will be pretty clear about significant zeros. Okay. They're going to use scientific notation. So whenever zeros are considered significant, you're either going to see a decimal point at the end of the number. So let's say 560 with a decimal point. That shows you that there are 3 significant figures. Or the number is going to be written in scientific notation so that you know exactly how many significant figures there are. So if the measurement is 300 and only this first 0 is significant or measured, then it's going to be written as 3.0 times 10 to the second meters. That way there's no confusion. You can get your number of sig figs from the coefficient, and you know that there are 2. So you won't have to question how many significant figures there are when you're dealing with zeros at the end of a large number. So here's some more examples of scientific notation and significant figures that you can go through. We went through several examples, so I'm not going to go through this slide with painstaking detail. But I just want to remind you again that the zeros at the end of a large number are not significant unless there's a decimal point. Okay, so you can notice there's no decimal point here, there's no decimal point here. So there's only 1 sig fig in the first value and 2 sig figs in the second. And zeros at the beginning of a decimal number are also placeholders. So all these zeros don't count, and all these zeros do not count. So keep that in mind. Here's a learning check. So you're going to identify the significant and non-significant zeros in each of these numbers and write them in correct scientific notation. So when you write them in scientific notation, you're already kind of acknowledging which zeros are significant and which aren't, because the non-significant zeros should not end up in your answer. So take a second, pause the video, and try writing these numbers in scientific notation. Remember that you're going to have this format. That's what you're shooting for. Pause it, give it a shot. Then rejoin me, and see what the answers are. So for A, the only ones that we're considering are these last 4 digits. So there are 4 sig figs here. When we write it in scientific notation, our coefficient is 2.650. That 0 is significant, so we have to include it. And then we figure out what our power of 10 is. 1, 2, 3. And since our number is less than 1, we have to throw a negative sign in there. For letter B, all of these digits are significant, including this 0, because it is between 2 non-zero digits, and there's that decimal point there. So that means that we have 5 sig figs. In order to make our coefficient, we're going to move that decimal point 1 time to the left. So you see here, boop, just the 1. And that number is bigger than 1. So, and it's positive, we're done. And don't forget units like I did. So the first one is meters, second one is grams. For letter C, there's only 4 sig figs. These other zeros at the end are placeholders. So we can drop a decimal point here just to visualize it, but for the purposes of significant figures, remember, it's not really there. We're going to make our coefficient and then figure out how many decimal places that is. 1, 2, 3, 4, 5, 6. And since this number is definitely bigger than 1, our n is going to be positive. And we don't forget our units. So there's significant and non-significant zeros, counting significant figures in a measurement, and writing scientific notation. All of those concepts wrapped into one question. So far, we've covered units of measurement, and we've covered significant figures and scientific notation. Now we have to talk about significant figures in calculation. So we can figure out how many sig figs we need in terms of measuring something with a ruler or using a graduated cylinder, because we know how many significant figures we can get from those instruments. But you're not just going to measure something and then call it a day. Oftentimes you're measuring something so that you can do a calculation. So we need to set up some rules for rounding and giving the correct number of significant figures for a calculated answer. Well, first, to review rounding. I'm sure you've gone over this. You've done this in high school. But sometimes you just got to brush the cobwebs off, okay? So the 2 rules that we have for rounding. The first digit to be dropped is 4 or less. Then that digit and everything else gets dropped. If the first digit to be dropped is 5 or greater, then the last digit that you're retaining is going to be increased by 1. So let's go through and do some examples. Here's the number that we're rounding off in the first column, and we're going to write this number with 3 significant figures and 4 significant figures. So for 3 significant figures, what we're looking at, we're retaining the 8.42, and we're looking at the 3 to see whether or not we're going to round up or we're just going to drop. So the first digit to be dropped is less than 4. It's 4 or less. So we just drop it all off. 8.42. For 2 significant figures, let's do this in a different color so you can see it. we're looking at 8.4 and then looking to the 2 to see whether or not we have to drop everything or increase by 1. 2 is definitely 4 or less, so we're just going to drop it. 8.4. If you want, you can take a second and pause and do the other two numbers, and then you can make sure that you got it right. So for 3 significant figures, we are looking at the 7. That's our last retained digit. We're going to look at the 8 to see whether or not we round up or we drop everything. 8 is 5 or greater, so we're going to bump up that last retained digit. So it'll be 14.8 that we record. If we wanted 2 significant figures, the 4 would be our last retained digit, and we'd be looking at the 7 to see whether or not we're going to bump it up or drop. 7 is 5 or greater, so we're going to bump it up. 2 significant figures, you're going to write 15. In our last example, 3,256. For 3 significant figures, we're looking at the 5. Make my mark. So, we look at the 6. 6 is 5 or greater, so we're going to bump that 5 up. 3, 2, 6. We have to add a 0. If we don't add that 0, we just have 326. And that's different from 3,250 something, okay? So, when you're rounding a number like this, you need to make sure that you add placeholder zeros where necessary. For 2 significant figures, we're looking at the 2. So we look at the 5 to see whether or not we're going to round up or just drop. 5 is 5 or greater, so we're going to round that 2 up to a 3, and then we still have to add our placeholder zeros, because 33 is different from 3,300. So you can add placeholder zeros and still retain the number of significant figures that you need. Make sure that you understand this last one. That's the trickiest. So there's rules for multiplying and dividing, and there's also rules for addition and subtraction in terms of determining how many significant figures you're supposed to report at the end. So for multiplication or division, your final answer is going to have the same number of significant figures as the measurement in the problem with the fewest significant figures. So let's say that we had these two measured numbers, 24.66 and 0.35. Well, these are 2 measurements, and we can count how many sig-figs there are. There's 4 sig-figs in the first number and 2 sig-figs in the second number. That means you're going to report your answer with 2 sig-figs, because of the 2 measurements that we have, 2 sig-figs is the fewest sig-figs. So that's the number of significant figures that we can trust. When you do the multiplication, your calculator doesn't care about sig-figs. It will give you all the numbers. It won't tell you units, and it won't tell you sig-figs. It will just give you whatever the answer is. You will need to say, okay, I need 2 sig-figs, so that means that I'm going to have to round this 6. Let me look at the 3. Okay, that's 4 or less, so I got to drop everything else off, and then I need to report my answer as 8.6. And then I have to write my unit, centimeters squared, because I'm doing centimeters times centimeters. So your calculator can only help you with so much. you have to remember the rules for sig figs, for rounding, and your units. So calculators are great tools, but they're not the end-all be-all. Here's another example. So this time we're doing multiplication and we're doing division all together. We've got 3 sig figs, 2 sig figs, and 3 sig figs, which I know is already written down, but I like to write too. So when you're doing this, you're going to have to limit your answer to 2 sig figs because that's the fewest. Your calculator is going to tell you some long number. Don't you tell me that long number, because it will be wrong, long and wrong, okay? Give me 2 significant figures, and don't forget your units. This time we did centimeters times centimeters divided by centimeters. And when you do all that out with your unit analysis, you should just have centimeters at the end. So don't forget, the calculator will always tell you what you want to hear, those sweet nothings and everything else. And if this answer and this answer were available for you to choose from, this answer here would be wrong, even though that's what your calculator said. The right answer is the one with 2 sig figs. Don't fall into the trap. Now we're moving on to adding significant zeros when we're doing multiplication and division and we need to report our answer with a certain number of sig figs. So in this example, we're dividing 6 grams by 2 grams. We've got 2 sig figs at the top, 3 sig figs at the bottom. Now 6 divided by 2, I hope you don't have to pull out your calculator for that. But if you do, it's just going to tell you 3, okay? No decimal point, no zeros, no nothing. We have to put some kind of zeros because we're supposed to report our answer with 2 sig figs. And that only has 1 sig fig. So you have to add a 0. In this case, you're going to add a decimal point in a 0. So don't get trapped by your calculator. Calculators are thirst traps, okay? Don't fall for it. It can tell you part of the answer, not all of the answer. Got to use your brain for the rest. So here's a learning check. Pause, take a second, do the calculation, and then report your answer with the correct number of significant figures. We'll go through it a little bit just to give you a hint. This first value, we've got 3 sig figs. Second one, we've got 4 sig figs. Third one, we've got 2 sig figs. It's up to you to figure out how many sig figs you should report your answer with. Do the math, report it, and then check your work. So hopefully you have done it. Here's our solution, okay? So we went over the sig figs. We've got 3 sig figs, 4 sig figs, 2 sig figs, okay? When we do our multiplication, we can only have 3 sig figs up here. When we multiply 5 centimeters by 3.408 centimeters. When you divide by the 2 centimeters, that's only 2 sig figs here. So our answer has to have 2 significant figures. When you do that, you should be reporting 8.5 centimeters. And make sure that makes sense to you. Now we're moving on to addition and subtraction, and this is different from multiplication and division. Multiplication and division, that's pretty easy. Addition and subtraction, the rule is slightly different. So your final answer has to have the same number of decimal places as the measurement with the fewest decimal places. So we're not talking about significant figures, we're talking about decimal places. And this is a good time to review those decimal places from chapter 1. So in our first example, our first measurement has the thousandths place. The second number has the hundredths place. The third number has the tenth place. Now, when I'm doing addition like this, I like to line it up as you see. And then I draw a line, just a dotted line, that shows me where my last retained digit is and where I'm looking to round. So we can only report up to the tenth place because that's the measurement that has the fewest decimal places. Okay, we only have up to the tenth place. So you do your addition with your calculator or by hand, and you get 66.102. But you have to round your answer to the tenth place. And my dotted line will remind you, oh yeah, I can't just put this answer. I need to round it. So you round your answer to the tenth place. Subtraction, same deal. You look at, okay, I've got the hundredths place, I've got the tenth place. I like to draw my line and then use your calculator or do it by hand. Your calculator is going to tell you 62.09. But you need to know, all right, I need to round to the tenth place because that's as many decimal places as I have in my measurement with the fewest number of decimal places. So you're going to round. You're going to say, okay, I've got a 0 here. Next to it is a 9. That's 5 or more. So I'm going to round that 0 up to a 1. That's addition and subtraction. So let's do the learning check. You have these two numbers, okay? You've got 82.409 milligrams and 22.0 milligrams. So you notice, okay, I am adding two measurements. I need to answer with the correct number of sig figs. So I need to make sure that I'm rounding off or adding zeros as I need to. Pause, try this problem, and then look at the solution. So pause it. Pause it now. Okay. Oops, why did I go ahead? So the first thing we're going to do is figure out what place it is that we need to round to. Here we've got up to the thousandths place. For our second measurement, we only have up to the tenth place. It's not lined up super well here, but there's my line. So I'm going to bring down the 0.9. I'm also going to bring down the milligrams so I don't forget. So we've just added it all together. Your calculator should tell you 104.409. It's not going to tell you milligrams. Now you have to say, all right, I need to round this number to the tenth place. This 4 is my last retained digit. I'm looking at the next digit, which is a 0. Do I have to round up or do I just drop? In this case, we're going to drop because it's 4 or less. So our reported answer is 104.4 milligrams. So make sure you know the difference between multiplication and division and addition and subtraction in terms of the rules for doing these math operations with significant figures. So now we're moving on to prefixes and equalities. We covered the units of measurements. We talked about measured numbers versus exact numbers and significant figures associated with the measured numbers. Now we're going to talk about prefixes and equalities. So that has more to do with exact numbers, particularly the equalities part. So we're going to be able to use numerical values of the prefixes to write metric equalities, and you'll see what that means in a minute. So prefixes are put in front of any unit in the metric system to increase or decrease its size by some factor of 10. So an example would be to use milli and micro, all right? So that can take a gram and make it smaller. So milligram or microgram. Notice how this is not a regular M. That's actually the Greek character mu. So it's got a little tail. In medicine and in other places, you may see micro abbreviated as MCG. And that's just for clarity. You don't want to get it confused with the milligram, as those are two wildly different measurements. These are the prefixes for the metric and SI units to increase the size of a unit. Okay? So if you're talking about a gram, or we're talking about seconds, meters, any of those units that we've described before to talk about volume and time and all those things, we can increase the size of that unit by adding one of these prefixes. And you'll notice that we've got the scientific notation here and sample equalities. So that's going to be important. The one that you may be most familiar with that you've heard of is kilo, like a kilogram. When you're at the doctor's office, they may report your weight in pounds and kilograms. If you have ever been there for a baby's checkup, they always do the weight in grams, not pounds. They'll tell you how many pounds and ounces and whatever, but the record is always in grams. Okay. This table tells you all the prefixes that decrease the unit. So we're talking about having grams or liters, seconds, whatever it is, and then we're taking that and making it smaller. So you've heard of a centimeter, I'm sure. That is smaller than a meter. And that's because centi means 0.01. Okay, so that's 100th of a meter. The relationship of a prefix to a unit can be expressed with that numerical value on the table. So kilo means 1,000. So if I have a kilometer, that means 1,000 meters, or 10 to the third meters. Same thing with liters. A kiloliter is 1,000 liters. A kilogram is 1,000 grams. So the kilo part is always going to be 1,000. No matter what other unit comes behind it, it's going to be 1,000, whatever that unit is. So let's do a little practice. If we have a picometer, what does that mean in meters? Now I kind of put together this little table so that we didn't have to go back and forth, but you may want to put this table, both of those tables, into your notes, maybe print it out or redraw it in your notebook so that you have it to access when you're doing your homework. So we look for pico. This is the numerical value. That's quite a few zeros. This is the scientific notation. I'm going to go with writing the scientific notation because that's a little bit shorter. So that's 10 to the 12 minus 12 meters. A petaliter, we find peta. The numerical value, again, that's a lot of zeros. I'm not going to write all those zeros. I'm going to use the scientific notation. That's saying 1 petaliter is equal to 10 to the 15 liters. And finally, microgram. We could remember, you can see it as that, or with the little mu that has the tail. Okay. Micro means 10 to the minus 6. So that's 10 to the minus 6 grams. That's how you can go from the prefix to writing an equality. We'll do more practice of that in class, but make sure that you can read the table to be able to make an equality. One place that you're going to see these different units, milligrams, grams, micrograms, if you take a daily vitamin, you're going to see all these different nutrients, and then it's going to tell you the amounts that's in the vitamin, right? You're going to see grams, you're going to see milligrams, micrograms, all these different measurements. So understanding these prefixes will help you understand the relative amount of the different things that you're taking in that daily vitamin. I'm taking prenatals right now for obvious reasons. And so in my prenatal, it's got all those things listed and how much. So that's something you can pay attention to next time you're doing vitamin shopping or just looking at the nutrition facts of certain foods. You may actually see the number of grams or milligrams like sodium or the number of grams of carbohydrates. Same deal. So let's talk about measuring length. Okay. Now the eye doctor, which that's an ophthalmologist, okay, the eye doctor, you can measure the diameter of the retina of your eye. A surgeon may measure the length of a nerve using a different unit. So we might have centimeters for one and millimeters for another. Each of the equalities that you see describe the same length in a different unit. Okay? So we've got 1 meter is equal to 100 centimeters. You can get that directly from the chart, right? Because centi means 0.01 meters. So if you want to have 1 whole meter, you have to multiply by 100. And that gives you 1 meter. 1 meter is equal to 1,000 millimeters. Remember that milli is 10 to the minus 3. So to have 1 whole millimeter, you need, or 1 whole meter, you need to have 1,000 millimeters. If you have 1 centimeter, you're going to need to have 10 millimeters, because the difference between these two, we've got 10 to the minus 2 meters and 10 to the minus 3 meters when we're talking about a centimeter versus a millimeter. So there's a power of 10 difference. This last one is a little bit trickier to understand than the other two. For volumes, typically we're talking about a liter or less in terms of the health sciences. You'll see deciliter a lot when it comes to blood plasma. You'll see deciliter. So here are some more examples of volume equalities, like going from 1 liter to how many deciliters that is, or how many milliliters that is, and things of that nature. So you're going to need to be able to write these kinds of equalities. This is an example of how you might see some of these volumes if you're looking at lab test results, right? So it's normal to get blood work done every few years just to make sure that your cholesterol is okay, looking at your iron content, all those kinds of things. Make sure you're not anemic. So there's ranges for the amount of certain things in your blood to be normal. And if they're elevated or if they're kind of low, then there may be something to investigate there. So this is just a real life application of understanding the different units that we've been talking about. Now we're moving on to another method of volume, which is the cubic centimeter. Okay, it's abbreviated as the CM3 or the CC, which you may have seen if you've ever gotten a vaccine or a flu shot. Those syringes usually have CC on them. Okay, it's the same thing as a milliliter. You can interchange them without problem. But in the medical field, you're probably going to see CC. The volume of 1 liter is defined by the volume of a 10 centimeter cube. So it's a cube that measures 10 centimeters on all its sides. And when you do that, you multiply all three of those 10 centimeters by 10 centimeters by 10 centimeters, you get 1,000 centimeters cubed as the volume. So that's where that unit comes from. And just from our equalities in the table, we know that a milliliter is 10 to the minus 3. So in order to have 1 liter, we have to have 10 to the third milliliters. So that's how you can equate the two, the centimeters cubed and the milliliter. Same thing with mass. So when you're measuring mass, you can write different equalities. And these are some examples of the equalities that you can write. So let's identify the unit that's larger in each of these pairings. And this will help when it comes to writing equalities. So take a second and pause, and then do the problem, and we'll go over it. I'm going to circle the unit that is larger, and let's make sure that you're doing the larger unit, not the smaller unit. So a millimeter versus a centimeter. The definition of a millimeter would be 10 to the minus 3 meters, whereas a centimeter is 10 to the minus 2. So a centimeter is larger. Kilogram, we're talking about 10 to the third grams, versus a centigram, which is 10 to the minus 2 grams. So a kilogram is going to be bigger. And all these numbers that it seems like I'm pulling them out of the sky, it's that chart that I showed you near the beginning of this lecture that has all of the different units and then the scientific notation and the numerical value for what it means. So if you need help with that, just pull up that chart. Okay? That may be another one that you want to print out and put in your notebook so you can access it more easily. For C, we've got milli versus micro. So milli, like we said before, is 10 to the minus 3. Micro is 10 to the minus 6. So the bigger one is going to be milliliter. And then finally, in D, we've got kiloliters, which is 10 to the third. And remember, this MC is the same thing as the mu. So that's for micro, and that's 10 to the minus 6. So the kiloliter is bigger. Make sure that you get those prefixes, that you know how to look at the table and use it, and how to identify it. We're doing all of this to lead up to writing conversion factors. And this is going to be the last section that we cover in this video. The next video will cover the remaining two sections of Chapter 2, but I didn't want the video to be too long. So you're going to need all of this information for the next video to make sense. The conversion factors are going to take an equality, like we were writing before, and write kind of something that looks like fractions to be able to convert between one unit and another. So we need to learn how to write equalities. You can use an equality to describe the same measured amount in two different units. So one example of that would be a pound. 1 pound of something is the same as saying 16 ounces. Same thing, it's a definition. You can also use equalities to write a relationship between the metric system, the US system, or between the two. So you can write a metric system equality, or a metric equality. 1 meter is equal to 1,000 millimeters. That's an equality. And both of those units are metric units. Or you can write something to convert between US units and metric units. So 2.20 pounds is equal to 1 kilogram. So there's the US and there's the metric. So all an equality is it defines a relationship between a measured amount. So you take a measured amount of one thing, what is it in another unit? Let's do a little bit more practice. So have that table handy because it will help you. Let's fill in these blanks. You can pause and try to fill it in on your own, and then watch me as I fill it in. 1 meter is equal to how many centimeters? On the table, you're going to see 10 to the minus 2 for centi. That means that we're going from this centi unit, which is smaller, to describe 1 meter. 1 meter is bigger. So we have to have 100 centimeters to equal 1 meter. The numerical value would be 0.01 meters is equal to 1 centimeter. Okay. 1,000 grams is equal to how many kilograms? Well, a kilogram is bigger for sure. And for a kilogram, that's 10 to the third grams, which is equal to, 1 kilogram, or 1,000 grams. That's what I was starting to write. So we fill in a 1 here. So you have to learn how to use that chart. We can take those equalities, which equalities have an equal sign, and write fractions that are called conversion factors. And those conversion factors allow us to do some math, which we'll get to in the next video. So let's say you have the equality 60 minutes is equal to 1 hour. We know that, right? So you can write two fractions from this equality. You can put the 60 minutes in the numerator and the 1 hour in the denominator, and then you can flip it. Have 1 hour in the numerator and 60 minutes in the denominator. It's as easy as that. I think that getting the equality is harder. Okay. Once you have the equality, you can write two fractions from it. So another example would be, we have this equality, 1 meter is equal to 100 centimeters. You take one number, put it in the numerator, put the other one in the denominator. Then you flip it for the second conversion factor. And we already did this one, so we're not going to redo this top one, but we can do this bottom one. So 1,000 grams is equal to 1 kilogram. We can write two conversion factors. There's one conversion factor. You flip it. For the second conversion factor. So you can always write two conversion factors for any equality. Now let's talk about conversion factors and significant figures. If you have an equality that's got two units that are the same, so if we're talking two metric units or two US system units, we're talking about exact numbers. So the example would be 1 pound is equal to 16 ounces. Those are exact, okay? Definitions are also exact. So defining what something is, that's an exact number. But if you have an equality between the metric and the US system, so let's say the 2.20 pounds is equal to 1 kilogram, then you're going to have one number that's obtained by measurement and then the other one that is exact. So you're going to have a measurement which has significant figures involved in this equality. The one exception is 1 inch equals 2.54 centimeters. That's been defined as an exact relationship. This table with some common equalities, you absolutely want this in your notebook. You're going to be referring to this when you're doing your homework. It will help you. So please, please, please print it out, slap it in your notebook, or at least if you have the book, you want to mark that page, put a little tab or something so that you can open it up real easy, but you want easy access to this table. So now we're going to talk specifically about metric conversion factors. So we'll continue using our example with 1 meter is equal to 100 centimeters. Remember that this is called an equality. And from there, you can write conversion factors. And they look like fractions. The 100 and the 1, those are exact numbers. So if you're using this, you would not be using the number of sig figs in the 100 or the number of sig figs in the 1 to determine sig figs for a calculated answer. Here's an example of the US system and metric conversion factor. So I used this example a little bit earlier. We have our equality, and then we have our conversion factors. You will oftentimes, if you're buying food at the grocery store, see both the ounces and the grams. So you can use one of these conversion factors to actually go between the two. In this case, you would have a measured number, so this would be measured. And we do care about sig figs there. So why don't you try writing the conversion factors from the equality for each of the following. And I shrunk the table down a little bit so that you could have it on this page, but you should already have it in your notebook or make plans to do so. Okay? So use the table to write conversion factors for each of the following. We've got liters and milliliters, meters and inches, meters and kilometers. Pause it, take a second, do it, then come back. For A, we've got liters and milliliters. That one is right here. So the equality is 1 liter equals 1,000 milliliters. To write our conversion factors, we're just going to make it like a fraction. And then we're going to flip it. B, we're going from meters to inches. So that we're going metric to US. That one's right here. 1 meter is equal to 39.4 inches. Write one fraction, and don't forget your units. If you don't have units here, then it's not a conversion factor. So that's for B. For part C, meters and kilometers. So 1 kilometer is equal to 1,000 meters. Write one fraction, then you flip it. So that's writing conversion factors from the equality. Keep this table, table 2.7. It will help your life. So here are all the answers written out very nicely, along with the equalities. I just wanted to show you how you could do it on your own using that table before I showed you the nice prettified version. Okay. So you can also see an equality stated within a problem that you can use to solve said problem. So if we're talking about a car traveling at a speed of 85 kilometers per hour, then the equality is 1 hour equals 85 kilometers. And you can write conversion factors. The 85 is what's measured. You have two significant figures there. And the 1 hour is exact. Because the measurement is, you're in the car, you have the speedometer. That's a measurement. But the 1 hour, that's just kind of convention for how we report these things. 1 hour is exact. Now the price of onions is $1.24 per pound, which is expensive. Not paying a dime or a penny over 99 cents a pound for some onions, okay? But if you do, that's your business. They must be some fancy onions. You can write an equality. 1 pound is equal to $1.24. Then write your conversion factors. And that $1.24 is the measured part, okay? So these are not definitions like we were talking about before. They are equalities, but they're not defining anything. So you have a measured number as part of it, and you will have to use it when it comes to sig figs. One thing that you should definitely be thinking about if you're in the medical field is dosage, okay? Whenever you take a pill like ibuprofen or Tylenol or something like that, there's a different amount of medicine in the pill depending on the size of the pill. So you might have a 250 milligram capsule, or maybe you got your wisdom teeth extracted and they give you a prescription for like 400 milligram ibuprofen or something like that you can't get over the counter. So here we've got an example of cephalexin, which is an antibiotic that's used to clear up respiratory and ear infections. And you can get it in 250 milligram capsules. You can say one capsule is equal to 250 milligrams, and that's the equality here. From there, you can write your conversion factors, and we know that the 250 milligrams is measured. When they're making the tablets, or excuse me, the capsules, that amount is measured quite accurately and pillified, okay? You can also have conversion factors from percentages. So we covered percentages a little bit, I believe, in chapter 1 to talk about, what a percentage is, part over a whole, right? But we can also write that as a conversion factor. So the example is a person might have 18% body fat by mass. We can write this as a conversion factor. Since we're talking about mass, we're going to use grams. So let's say that you have 18 grams of body fat, which that 18 is from the percentage. It's always out of 100. So let's say you call it body, right? But 18 grams of your body is fat for every 100 grams of your person, okay, if you have 18% body fat. That's how you can write a conversion factor. You can also flip it, just like you do any other conversion factor. So if you're solving a problem, you can use either of these conversion factors to go from the, if you have, let's say that your mass is this much and you're trying to figure out how much body fat that means, or you have a certain amount of body fat and you're trying to figure out what that means in terms of what someone's mass is. So you can use your conversion factors to do either one of those problems. When we're talking about really small ratios, we're talking about parts per million and parts per billion. You see that a lot with environmental sciences. So something like, the amount of contaminants in your water might be reported as parts per million or parts per billion, okay? Very, very small amounts. So let's do a learning check. Write the equality and its corresponding conversion factors. Identify each number as exact or give its significant figures in the following statement. Salmon contains 1.9% omega-3 fatty acids. So we need to write a conversion factor and then identify the parts as either being an exact number or measurement and give the sig figs for the measurement. I like salmon. I had salmon a couple of nights ago. Healthy fish and delicious. Let's write a conversion factor. We know that percentages means part out of a whole, and that the whole in this case was going to be 100. So on the top, we're going to have 1.9, let's say, grams of omega-3 out of 100 grams of salmon, because the salmon is the whole thing. Out of all the things that salmon is made of, 1.9 grams out of every 100 grams is going to be omega-3 fatty acids. Now the question is, which one of these is exact? Which one of these is measured? This 100 grams is exact. It's part of the definition of a percentage, right? The 1.9 grams is measured. Someone had to figure that out. It's not something you count. It's not part of the definition. How many significant figures does it have? There are 2 sig figs. So that's how you take a percentage, write it as a conversion factor. That's only one conversion factor. We also need to remember to flip it. So there you go. Please watch the next video. It's going to cover the remaining sections of Chapter 2. Here we went through sections 2.1 through 2.5. We still have to cover 2.6 and 2.7, which is taking all of these concepts of looking at the identifying sig figs, learning how to do the multiplication, division, addition, subtraction with sig figs, writing equalities and conversion factors. We're going to combine all of those things to be able to convert from one unit to another. So I didn't want to bog you down too much because this lecture is already about an hour and a half long. You may need to take a break and do something else. I know I would like to. So that's all right. Just make sure that you watch both videos for class on Tuesday. Until then, I'll see you.